Good morning students, myself Sushmita, Assistant Professor EC Department RCTE. So in this session we will be learning about reflector antennas. So on completing this particular video you will be able to understand what is reflector antenna and what are the different types of corner reflectors, also method of image formation using reflector antennas. So first thing, reflector antenna. So what is reflector antenna? It is one of the most important antenna that is used in microwave radiation applications. So we can say that at microwave frequency the size of the antenna will be small and the frequency and size will be inversely proportional. So depending upon the shape of the antenna, that is the reflector antenna, it will be producing the desired directivity. So what we can do is we can go for designing a reflector antenna to produce the directivity in the required direction that we need, or the desired direction that we need. So in a reflector antenna we need another antenna to excite that particular antenna. So for example, we can go for using dipole, horn or slat antenna which can be used to excite. So this excitation antenna which are used for exciting this reflector antennas are called as primary antenna, and that reflector can be called as secondary antennas. So usually this reflector can be of any shape. So while coming to the next slides we can see how they are how the different shapes of reflectors are present, and the most commonly geometric shapes that we are using are, it can be either plane or corner, or it can be curved or parabolic. So flat sheet reflector or plane reflector. First type is flat sheet reflector or plane reflector. It is the simplest form of reflector antenna and it is kept in front of the feed. So what will happen is the energy is made to radiate in the desired direction. So if you want to increase the directivity, then large flat sheet has to be placed in front of the half wave dipole. So this is how we can go for increasing the directivity on the flat sheet reflector. So one of the main advantages, we can go for reducing the backward direction, since this particular flat sheet will acting as an obstacle so that it do not radiate in the backward direction. At the same time it will be increasing the gain in the forward direction. That is one of the major advantage of using flat sheet reflector or plane reflector. So this is the diagram. You can see plane reflector. So where the feed is kept at the center point, the incident ray is made to fall on the sheet and it is again reflected back and towards the wall. Next one is half wave dipole with plane reflector. So this is nothing but we will be having a plane reflector and all those things will be taken into consideration. Okay, so this is how it works. And next thing is half wave dipole array with plane reflector. So we will be having half wave dipoles as well as the field pattern, and half wave dipole with reflector environment. Okay, so next what we have to do is we have to go for half wave dipole with reflector element. So these are the four possible ways that we can use. Next thing is corner reflector. So one of the major disadvantage of flat reflector is backside or back and side radiation. So that is one of the disadvantage of corner reflector. So what we are doing is we are going to modify and join two flat reflector with some angle concentration such that the radiation is made in the forward direction. So we are going to make some changes by joining the two flat reflector. This particular thing is called as corner reflector. Angle is called as include angle. So angle is 90 degree and sometime angle other than 90 degrees also. So you can see in the diagram corner reflector top view and then corner reflector front view. So this is how we will be placing the feed element. It can be placed at the center, and in the front view you can see that it is at the right side of the reflector. So actually in general there are two types of corner reflector. One is active and another one is passive. Active is nothing but with source and passive is nothing but without source. So as the name indicates, we can say that there are two types of. So let's see in detail one by one. So this is vertical corner reflections with field pattern along the main axis. So initially we saw that is the front side as well as the front view as well as the side view. So this is a vertical corner reflections. So here also you can see that flat sheets and then driven elements as well as the corner angle. So next one is system efficiency. So the system efficiency, that is the output we are obtaining, will be mainly depending upon the spacing between the vertex of the reflector as well as the feed element. So that particular distance is called as D. So distance, how we can adjust? We can adjust by including the angle. Initially we saw, no, in corner reflector we can either go for adding, or either we can go for joining at the ends, and we can go and create an angle. So the same case applies here too. So we can adjust the distance by including the angle. So while including, the angle either decreases and the spacing between the feed and the reflector will be getting increased. So that is how we can go for improving the efficiency of the system. So next thing is, most of the time feed element is dipole or array of collinear dipole that is placed parallel to the vertex, which is placed at the distance d. So the mainly the dimensions that we are considering are aperture of reflector antenna dA and the length of the reflector as well as height of the reflector. These three dimensions are taken into considerations. These three dimensions are taken into consideration, where dA is lambda less than 2 lambda and lambda by 3, which is less than distance 2 lambda by 3, and L is equal to 2D. This is how it works. Now coming to the analysis of radiation field of source with corner reflector, we can give that alpha is equal to pi by n. What is pi? It is just the value, and where n is the integer. Now what we are going to do is, we are going to apply image principle. So what is happening? Field that is being produced between the corner element, that is the corner reflector, will be same as the two n current elements, which is equally spaced, that is equidistant on circular path with a radius r. So here the number of images, polarities and the position will be completely depending upon the include angle and the polarization feed element. So multiple images on circular path will be formed for different angles. So we can just change the angle at different dimension, and we can go for obtaining different multiple images at circular paths. So you can see here I have changed to 3 different angles, and alpha is equal to 90 degree, alpha is equal to 60 degree, and alpha is equal to 45 degree. So there are different variations. Next one is corner angle. So as we saw earlier, corner angle will be depending upon the integer n. So now I am representing 3 different conditions for corner angle alpha with different values of n. Alpha is equal to pi by 1, where radiant is equal to pi or 180 degree, pi by 2 or which is 90 degree. So this condition, when alpha is equal to pi, it applies for flat sheet or plane reflector. Similarly, when alpha is equal to 90 degree, this applies for square corner reflector, and when alpha is equal to 60 degree, this applies for corner reflector with corner angle alpha is equal to 60 degree. So now let's see some methods for images, how to form in square corner reflector. So first, initially what we have to do is, we have to consider a corner angle of alpha is equal to 90 degree. So this particular reflector, it will be having one driven element which is located at the point P. You can see in the PPT clearly. So this is will be representing the driven element, and it is represented by points 2, 3 and 4. You can see in the diagram 2, 3 and 4 are the driven elements. So the driven element will, which is nothing but it will be carrying the current of same magnitude all throughout the images. So the current in the driven antenna in the image is said to be in phase, while the current in the image 3 and 4, that is towards the center point, are said to be out of phase by 180 degree. So this is how image is being formed. So we have a particular mathematical representation of this electric field in horizontal plane, where E phi of theta is equal to k dash I1 cos alpha d cos theta minus cos alpha d sin theta, where I1 is the current in each element and k dash is the constant incorporating distance r, where d is the distance of driven element from the corner along the main axis. So now we have calculated the horizontal plane electric field. What I am going to do now, I am going to calculate the vertical or terminal voltage at the center of driven element. So this in terms is given by V1 is equal to I1 plus Z11 plus I1 Z12 minus I1 Z13 minus I1 Z14. This is the equation. So Z11, what is Z11? It is nothing but self impedance of driven element. Z12 mutual impedance between elements 1 and 2. Z13 mutual impedance of elements between 1 and 3 as well as 1 and 4. So this is how we can write the terminal voltage. So now coming to the calculation of power, if P is the power supplied to the driven element, then the power input to the each image also will be P only. So how we are expressing in terms of current I is equal to, as we know that P is equal to I square R, similarly the same applies here too. So since we have mentioned it as I1, P is equal to I1 square into R. For 60-degree corner reflector, 1 driven and 5 images. For 45-degree corner reflector, 1 driven and 7 images. So depending upon this, the field strength will be changing according to the driven element, and we can form 3 image elements is 4 times of the field strength. So all the image elements can be added to the driven element. So power radiation of this particular corner antenna is 1.7 times the half-wave dipole, which is in free space. So the gain is calculated almost 90 dB or more. So now coming to the design equation of corner reflector antenna, the important dimension in the corner reflector antenna is as follows: dA is equal to dimension of aperture, d is equal to distance between feed and vertex of reflector, and L is equal to side length of reflector sheet. So d is equal to L by 2 or L is equal to 2d, that is just cross multiplying the denominator 2 to the numerator, and dA is equal to root of L square plus L square, which is added, and 2L square. Taking out the square, we get 2 root 2 into L. Root 2 is nothing but 1.414 into L. We already know that L is equal to 2D. So substituting the value of 2D, we get 2.828D. So this is the dA, dimension of aperture for a corner reflector antenna. So we can go for using equation 1 and 4 to design the corner reflector antenna, and these two equations are called as design equations of corner reflector. So I hope you all understood and had a useful session. Thank you.